Alright, this is going to be a walkthrough of lab number 21 on atomic spectra. This is a Java lab, and I know that Java can be kind of problematic, so if you can't get Java to work, then I hope you're here watching this. So what you can do is I'm going to essentially do the lab, and actually I'm going to time-lapse it to speed it up for you all, and that way you can make the observations and jot them down and complete the lab without having to get Java to work or something along those lines. So we're told to download this. We're going to go to one atom, spectrometer, squiggles, run, slow motion, and we're first going to mess around with a 2-atom guy. So let's go ahead and do that. Here's the lab, so spectrometer, that's going to show us the colors, run in slow motion, and we're going to go to a configurable guy. And what we are going to do is essentially going to fire electrons off of this guy right here. Technically it's called an anode, and it can interact with the atom. It can excite the atom. The amount of energy, well, we can mess around with the energy using this battery right here. And we're told to kind of drop this guy down to the middle. And the first thing we're going to do is we're not going to give the electrons enough energy to excite this atom. This right here is going to be the atom, or be the energy level of the atom. And if we don't have enough energy, then we can't excite this. So here, the energy of these electrons, not enough to excite the atom. And I can go ahead and crank this thing up, take it off running in slow motion, and what's going to happen is absolutely nothing. These electrons don't have enough energy to get this thing to work. So we kind of did this step right over there. What did we learn from this? Well, make your own judgment on that. Then we're going to mess around with the energy level so it does have enough energy to excite the atom. So what we can then kind of do is, I'm going to put it back into running in slow motion, increase the energy of these electrons. Now it's enough to excite this atom. And what you can kind of see is you can kind of see that some, not all of the electrons get absorbed, and it excites the atom. This is the electron kind of hopping up to that energy level. When that electron hops down, well, something really important happens. It's going to emit photons. And these photons always have a certain color, and that color is going to correspond to this energy difference. Technically, Planck constant multiplied by the frequency, converted over to wavelength. Never any other colors are going to come off of this. Now what we're told to do is we're told to go ahead and increase the energy level and make sure the battery has enough oomph to excite this guy. So I'm going to, first I'm going to increase this, and I'll go ahead and increase this, and now I'm going to reset my spectrometer. And what you can kind of see is as long as the electrons have enough energy, then we can excite the electron up to this energy level. Now, something to pay attention to is the color, and here we can only see one color. We only have one energy level, we only have one energy difference. We're only going to have one frequency or one wavelength come off of this. This is infrared, this is ultraviolet. In the language of energy, this is high energy, this is low energy. Not surprisingly, I increased the energy. Before it was right here, now it's right here. So these photons have higher energy. We can get burnt with ultraviolet, but not with infrared. Now we're told to go ahead and put 3 energy levels and reset the spectrometer. And let's go ahead and make our observations. So I'm going to boost this thing up to 3 energy levels, and I'm going to make sure this thing has enough juice to excite both of these energy levels. And I'll go ahead and take this thing off of slow motion, build up some statistics, and then we'll talk to it. Alright, that's probably good enough. Now what we're kind of seeing is we're actually seeing 3 colors coming off of this thing. We're going to have ultraviolet. That's going to correspond to this big energy difference. Lots of energy difference, lots of highly energetic photons coming off of this. So that's a 3-to-1 transition. We're also seeing a 3-to-2 transition, and that's kind of this cyan color right here. And that, again, that's going to correspond to this particular energy difference, that particular frequency. We're also seeing a 2-to-1, and that's going to probably correspond to these guys right here, although I'm not seeing any firing off of this thing. So 3 energy levels, we're going to have 3 colors. Now we're told to go ahead and go to hydrogen, and we can go ahead and speed this thing up. record the colors and the wavelength cut from the spectrometer, and don't really have to pay attention to the infrared and ultraviolet ones because we're not really able to see them anyway. So let me go ahead and change this thing over to hydrogen and reset this guy. We don't have enough energy to excite this hydrogen guy just yet, so I'm going to jack this thing all the way up. I'm going to allow this thing to speed up, and I'm probably going to time-lapse this for you. In fact, I will time-lapse this thing for you. Alright, I'll call that good enough on the time-lapse. Could wait a little bit longer. But what we're kind of seeing is we're seeing certain colors, and only those colors. We're seeing this color right here, which corresponds to a certain energy difference. This one corresponds to a certain energy difference. This one and this one. These are going to correspond to certain jumps within the atom, and you can kind of see those happening right here. This is particular to hydrogen. Hydrogen's electrons live in certain orbits, and these certain orbits are going to have certain energy levels. Therefore, the fingerprint of hydrogen, if you will, the photon fingerprint of hydrogen, if you'd like to call it that, is only going to have these colors and these colors only. Next, we're told to go ahead and do mercury. So what we're supposed to pay attention to is the colors and the wavelength. How is this different? If we had to differentiate between the two, what would we look for? So I'm going to, again, time-lapse this thing so you don't have to sit here and wait for it, and then we'll talk about what we see. Alright, I'll call that good enough, and what you're taking a look at is you're looking at mercury. You notice the lines over here are in different places. These different energy levels, and there's also more of them. You saw this one has 9. They're in different places. The gaps are different, therefore the energy of these photons are different, therefore the colors are different. And this is the photon fingerprint of mercury, if you will. It looks different from that of hydrogen. We're then told to go ahead and take a look at sodium, and then we're going to give neon a shot, and we're not going to see any photons, so we'll talk about that in a little bit. Here I'll put sodium on here, and we'll do a quick little time lapse. Alright, and we'll call that sodium. So now let's go to neon, and you can run this thing until the end of all days. What you can kind of see is even if I were to crank this battery all the way up for this particular setup, then I don't have enough energy, so I can't excite this particular gas inside of this tube, at least with this setup. Now, what we're told to do is we're told to go ahead and look up the spectrum for neon, so I'll trust that you can look to Dr. Google for that. And if we had a powerful enough electron, what colors would we see and what wavelengths would they be?